To start with this session, I will show you, first of all, the basics of programming with PyCOMPs, like how to start the runtime in a distributed environment, how to define a task, how to invoke a task, and how to stop the runtime. Okay, so first of all, think that we have a programming model for PyCOMPs, and this programming model is based on sequential Python code. So the main thing that you have to bear in mind is how to define the tasks. Okay, so in order to show you how to do this, I will use the integration with Jupyter Notebooks, but also don't worry, because in the session with Mare Nostrum, I will show also you how to do this with plain Python scripts, because they have a big difference. But for just to show you how to define tasks, I will use Jupyter. Okay, so let's get started with this simple example. With Jupyter Notebook, it's necessary to load the library for the integration of PyCOMPs with Jupyter Notebook, which is known as PyCOMPs Interactive. We used to call it iPyCOMPs. And the next step is to start the runtime. Please ignore these lines, and we will focus only in this else line, which is the line that starts the runtime. This ipycoms.starts accepts a lot of parameters that are used to configure the runtime when it starts. Like, for example, to define if you want to get the task dependency graph, the refresh rate of the monitor, if you want to put it in debug mode so that you get more information of what is happening under the hood, but this is more for debugging purposes, to get the trace for performance, but also other flags which allow you to deal with more complex infrastructures and so on. But for this first example, we will use only to define to get the task dependency graph and the monitor. Okay, once we run that line, it says that it has started PyCOMPS 2.8, which is the latest version that we released a couple of months ago, and it says where the logs are. Okay, this path is where the logs will be located. And now we are ready to play. The next step is to define tasks. Okay, to this end, since we are focused in sequential Python code, and we are going to use Python decorators. So importing the task decorator from the PyCOMPS library is the first step, and then we can use it on top of any function which will be considered the unit of a task, so the task code. Okay, in this first task, we are going to define a task that is going to be called square, that has one parameter, input parameter, that will be inferred automatically, and we say that it is going to return something. In this returns statement, you can say that it's going to return an integer, but since this is not very Pythonic, you can say that it is going to return one element. Okay? If it's going to return two elements, you can say the number of elements that it is going to return. In the best case, it will try, if nothing is said here, it will try to infer. But since that takes some cost, it is better to define. Okay, so we have the unit of work of a task, which is the multiplication, and we will execute this. Now we are going to define another task which has two input parameters, val2 and val3, and it is going to do the addition of those two parameters, and it's going to return the result. And we are going to define a third task, which is also going to accept two parameters, and it's going to return the multiplication of those two parameters. I want to point out at this moment that the task decorator accepts also other flags that will be shown later on. But for this one, we will only need this. And how we are going to invoke those tasks, like normal functions. So we are going to square like a function, a normal Python function. It will say that it has found a task. So the runtime has received that query to execute that task, and it has been spawned and uploaded into a worker node. Now we are going to run the second task, and we are going to run the third task. Okay, so I want you to take a look at these three calls that we have executed. We have first a call to square, which returns a parameter. This result, A, it's the input of add, okay? And add returns B, which is the input of multiply. The runtime automatically detects these dependencies among functions without the user interaction, builds the task dependency graph, and runs tasks and those functions in the workers respecting the task dependency, so that the validity of the execution is guaranteed. Okay? Finally, when the execution has finished, we can then stop the runtime, and at the end, if synchronize is true, it will retrieve all the objects that have been executed remotely, and we can check its results. Okay? Next, we are going to, mm, to a more complex example. In this second example, I will show you how to synchronize data. Okay, now that we know how to define the unit of work, which is a task, those tasks are going to be executed remotely. At some point, we will like to retrieve that data from that remote worker node to the main code, to the master node, so that we can play with it in the master, or even do any other transformation. As in the first notebook, we are going to start the runtime again. In this case, have also the graph here and tracing disabled. And we are going again to import the task decorator. We are going also to import the hints that we can use in the task decorator, which in this example are not very useful, by the way. I can remove them. And the main call to synchronize data, which is to retrieve data that has been generated remotely in a task. Okay, so once we have this, we are going also to define the same tasks as in the first example, in the first notebook, and we are going to call them in the same order as in the previous example. First we call to square, then we call add, and then multiply. Those tasks have been executed remotely, and A, B, and C have been produced in a worker node, which in my machine, it's in another process, but it can be in a remote node of the infrastructure. In order to access that data, we use the COMPSs function to retrieve it. So if we execute this command, we are able to deal with that value, and we can print its value. Here, we see that C has been retrieved, and it has been added 1, so it is 41. While A and B are still what we call future objects, which is the wrapper that we use to take the dependencies among them. A future object means that it has not yet been retrieved to the master, to the main code. So in order to retrieve that data, you can use, again, the COMPSs call, bring A, and then you get the result. At the end, You can also stop, bring everything which is left in the worker nodes, and you can print the entire results. Okay? Any question until now?
Yeah, well, the Bishak is asking if well if they have to have everything running, but the what you have to have it's all the things download, and in the next session you will explain how to start the Jupyter and
Yeah.
the notebooks, right, Javi?
Yes. In the next session, I will guide you to how to start everything. For now,
Okay.
it will be good for everybody to have only the Docker pool. And if you are not using the virtual machine, to install the PyCOMPSs player.
Okay.
Okay.
No more questions, I think.
Okay. Thank you, Jorge. Okay. So now I'm going to continue with the next notebook. Okay. Uh, in this next notebook, I'm going to show you how to use objects, lists, and synchronization all in the same place. Because until now, we know how to define a task and how to synchronize data, how to do a COMPSs wait on. This means that those two things, decorators and COMPSs wait on, are the basics, but there's much more, the language, Python is more rich, and you can also think about how am I going to define a task within a class, for example. Can I? The answer is yes, and I'm going to show you in a bit. First of all, let's start again the runtime. In this particular case, I am going to run in debug mode. If you run in debug mode, you will see in the output that it is going to show you and give you a lot of information. This information is very useful for us to determine if there are issues. I will show you this later on with more detail. And let's focus in the syntax. As I said before, we have the const wait on to retrieve data, and we have also another call for synchronization, which is the comps barrier. Comps barrier is a call that the user can put into the code, into the main code, to let the runtime wait until all the tasks that have been submitted until that point have finished. Okay? While in the const wait on, it waits only for the task that produces that result. Okay. Okay. So as I said before, a function can be declared as a task. Any function, even it is within a class, a user-defined class, can be defined as a task, and it can be used as a normal method of a task. So you just need to put on top of the function declaration the task decorator with its appropriate flags in the task decorator. I will give you more hints about this in the next notebooks to play with files and so on, but for now it's with this is okay. And um, for example, we can get and play with self, saying that the target direction it's going to be only input only. And since Jupyter Notebook it's a notebook, we are going to define it in a different module so that PyCOMPSs can pick it and execute it in remote. Okay, so think that in Jupyter we need to play a little bit with files, with writing them in files. So For example, we are going to define a shape class which has its constructor, and it has four tasks. For example, area, that returns the area of the contained parameters, the perimeter. It is also able to modify its inner values, and it can also do like print, do not modify the object. There's a difference between these two tasks. The difference is that this one is modifier, it's modifying the object itself, and this one is not. This one is only printing the contents. To this end, we can use the target direction flag into the task decorator within direction, with the direction, so that we let the runtime know that whenever this function is called, this task, its direction of the parameter itself, it's going to be input, so that it's going to construct the task dependency graph, taking that into account, and this will avoid to get further parallelism. But in the functions within classes that modify the object itself, it has to be by default, defined by default, which is input output. Okay? These directions are used to construct the appropriate task dependency graph. So if we run, it will write this into my shaper.py, and then we are now ready to play with it. So first of all, we import shape, and then let's create a list of shapes with two shapes. Now we want to get all areas. Imagine you have 1,000. In this case, we have two. We are want to get all areas. So we play with this class as a sequential Python code. We loop through all elements, and we are going to append calling to the area task, okay, which is defined here. Whenever we loop, the task has been submitted, and then we are ready to synchronize all areas to get all of them. If we wait for all of them and we print the result, the tasks have been submitted to the worker nodes. Each of them has computed one or more, and we can then print, we can retrieve the result and print them. Let's go with another usage of this class. We are going to define a rectangle. We are going to scale size, which is a task, which is modifying the rectangle. Then we want to call to the area, and then we are going to retrieve to synchronize the object itself. This comes weight on over rectangle will synchronize the object and its inner elements. So it will retrieve the actual element which has been modified by a worker. Then we are all ready to print the its x element and its area. In addition, we can have all perimeters that has been empty list. We can append the previously defined rectangle, and we can also append other calls to tasks. So in this example, we will have an object and a list of future objects that can also be retrieved all in one call, calling to the whole list with COMPSs. So COMPSs works with single objects, but it also works with iterative, that objects that can be iterated. So in this case, it has synchronized those two elements. And to finish, we stop the runtime again. It has found a few elements to synchronize, and that's it. Do you have any question until now?
Yes, there are two questions. Diego is asking, will PyCOMPs use type annotations if they exist? For instance, the return type?
That's a very good question. That's a very good question. Uh, because I guess that you are thinking in Python 3 type hinting. If there's type hinting, mm, we PyCOMPs will take that from the type hinting like this. I think it was like this. Okay, so this is exactly the same. But since Python 2 doesn't have type hinting, we keep the flag for the returns, for example, in the task decorators, so that PyCOMPS is compatible, backwards compatible with Python 2.
Okay. Is it asking your question, Diego? Answering your question, sorry.
Yeah, perfect. That was exactly what I was thinking of.
Okay.
Yes.
And Katarina is also asking, where do you say that it should run the code? On worker nodes or on the master?
The task, where did you say that it should run the code? The main code is running in the master node, while the task code, so the units of work defined within the task, are being executed in the worker nodes.
Uh, yeah, but where do you tell it that it should calculate like that? Like, is this like integral to PyComps? It should know that everything else should be done, run on workers, or do you actually say somewhere that it should?
Mm, to do this, we have well, it is the runtime who decides in which worker it's going to be executed each task. But the main code runs in the master, while the tasks in the workers. So I guess
All the tasks are going to be remotely executed.
yes.
Okay, so then later there are other decorators to indicate the constraints of the task, and then the scheduler could select one node that fulfills the constraints, but you will see later. I think it's in the inside the tutorial.
Yes,
Javi? Yes.
there's another with constraints and yes.
So by default, main code is in the master node, and the tasks, every method that you annotate as task is executed in the worker nodes, in the remote nodes.
Yeah, yeah, I understand that. I just don't understand when do I tell it which is my master node and which are my worker
Oh,
nodes.
Ah,
that,
okay.
that that's a good question.
Yeah.
But Jorge, you will explain this more tomorrow, no?
Yes, yes.
Yes.
Tomorrow in
Okay.
the execution environment sessions, we will explain this. Basically, we have a configuration file that we put the resources that we have available.
Ah, okay, okay, okay. I
Yes.
got it. Thanks.
Okay, but we will see later tomorrow.
Yes. In that file they put the resources and their configuration and their characteristics, so that the runtime is able to check to take the resource and to take the task to the resource that can be executed, where it can be executed.
Okay, no more questions so far.
Okay, so I'm going to quickly with defining classes and objects with reduce, which is very similar to the previous notebook. As again, with Jupyter Notebooks, we are going to start manually the runtime. Again, we do the imports that we need, the const return and the task decorator, and we use the same class as previously, but in this case, we also add the description parameter. This needs to be top description. Okay, so now we are going to define a task which is outside of the shape class, which is going to retrieve like multiple parameters. It's going to be like a list, and it's going to iterate over it to get the sum of all the elements, of all its inner elements. As in the previous case, we are going to define a list of shapes, and we call the constructors. We have a set of shapes. We are going to compute all areas, and we call to all elements to the area task. So at this point, what has happened is that the runtime has detected that there are 4 tasks calling area. They have been uploaded to the worker nodes, and in all areas, we have the future object that will be corresponding to the area. Now we are able to synchronize all of them, and we can see that the results have been retrieved. We can, again, this place with the one shape calling to the object itself, and we can finally, which is the difference with the previous notebook, to define a list of shapes and play with that function so that we have a, a task that retrieves a variable number of elements, which is the number of elements contained in all perimeters. This is also a supported feature, and in this cell, I am going to call add all tasks with the results calculated by all perimeter tasks and wait for all the results. It has found the task definition, and we have finished. So what these have done with these 2 cells that are the most important in this notebook is that it has been able to detect that you want to calculate the perimeter of all shapes. They are independent because there is no dependency among them, and we can have a single task that is going to receive the results of all those tasks, of all perimeter tasks, and calculate the accumulated sum of all of them. So very similar to the previous one. I'm going to shut down until now to have more. Finalizing with the task declaration, I'm going to show you one of the latest things that we have included, which is the using collections. A collection, well, first of all, let's start the runtime again. And I'm going to define what a collection is. A collection is a list of elements that can be anything, okay? So the runtime is also able to detect dependencies of its inner elements. Okay, so it's not only necessary to play with plain objects or single objects, so that PyCOMPS is also able to detect the dependencies that there are in the inner elements of a collection. Okay? The important thing here is to first import the library for the task decorator and the synchronization things. And whenever you're going to use the collection, here we have again the shape object with some slips, and at this time we have, I am going to base in the previous notebook, we have the same class, the same task, sorry, as in the previous example, which receives an asterisk, which is a variable number of elements, but this was supported until release 2.5. But since then, we included collection in, and a collection can be defined in the task decorator. This is why I said that the task decorator can include some more hints. And in defining that this parameter is a collection and its direction, which can be in or input output. We have the examples here. The runtime is going to take that into account with all its inner elements to respect the data dependencies. Okay, so if we have a task which is add all C, which is my list, let's perhaps also that one. We have another task which is add all C2, which has two return elements. See here, sum and sum2. It has two input parameters. Both of them are collections, and they are only input parameters, which means that they are not going to be modified within. And we have a last task, which is scale all, which is going to retrieve my list, which is a collection input output. It says that this function is going to modify my list and the amount to scale all elements of the list. Okay, so we have three tasks: one which receives a collection in, one which receives two collections input, and one which receives a collection input output. Again, we import shape, and we have an empty list. We define 4 shapes, and we want to get all areas. This is simple now. We just call all of them. We synchronize the results, and we can check that if they are fine. It has taken a little bit more because it included the sleeps here. Again, accessing data in collections. If I define an all perimeters empty list and I append an object, I can get all the results, and I am calling add all C. I can then call to the previous, like in the previous example, and get the result of all of them. However, since we have now support for collections, we can directly use collections, which is a more common way to use lists in Python instead of with the asterisk. So if we define two collections like all perimeter and all areas, and we use them in all C2, all perimeters and all areas are lists that contain feature objects that have been produced by all perimeter task and all area task. We can call add all C2 and store the results in my pair and my area. Once we have them, we can synchronize for their value and print the result. And we are also able to scatter data from a collection, which is we have a collection and we can iterate over any other task calling with the element of a collection, which will be equivalent to play with lists, to iterate with lists. Okay, so until now, I want you to take one thing into account. The only thing that we have included into the code are the task decorators with some hints, the returns, or if it's a collection or if it's not a collection, and the COMPS wait on. All other piece of code, like the main code, remains exactly as a sequential Python code. Okay? So, any question until now?
No, no questions.
Okay, so I'm going to be very brief in the next notebooks. Let me. Okay, let's change a little bit. Until now, we have seen how to play with objects like normal Python. But PyCOMPSs also supports to play with files, because we know that some of you have your applications, and imagine that you call a function with a file, and that function is going to modify that file. If that task is going to be executed remotely, we must tell that a parameter is a file to the runtime so that it can take the necessary actions, which, for instance, will be to transfer that file to the worker node so that the task can play with that file and retrieve the data back. Like, for example, if it's going to modify that file. The runtime, the COMPS runtime is able we are able to define that it's going to be a file, and it is able to play, for example, to deal for example, with that transference of the data from the master to the workers, or if it detects that it is going to be, that the file is in a shared storage, like, for example, GPFS or Lustre, it is going to not to move to transfer the data through the network. So the runtime is smart enough for that. In this case, we are going to see a very simple example of how to use files with PyCOMPSs. As you can imagine, we are only going to play with the task decorator again. To this end, we first import the task decorator, file in, file out, and file in output, input output, well, which we are going to use in the task decorator. File in is going to be used to define that a parameter, it's going to be filed with input direction, so that we are saying to the runtime that that task is not going to modify that file. If we define that a parameter is a file out, we say that that task is producing a file. And with file input output, we say that the task is going to modify an input parameter, and it's going to modify that one to produce for the later one. This directionality is what we use in the runtime to detect the data, to define the dependencies, and to exploit the parallelism. One thing that I forgot to mention previously is that the task dependency graph that we have set in the start, it's generated in the log files, and we will see that task dependency graph manually in hands-on, where I will guide you to take that file, plot, and see how those things are. Okay, so for now, we are focused only on the syntax, and then we will see how does the runtime works with that task dependency graph. So you can imagine we have a function which will write some content to a file. So it has two parameters, fout, which is defined as file output. The call to this function is the name of the file, and content is what we want to write into that file. Then we have another task, which is modifying a parameter, f_in_out. It will open, it will write something, and it will close the file. And later, finally, we have one task, which is for read files, which has one parameter, which is reading the file passed as a parameter and returns something, returns its content. Okay, so as you can imagine, it's as simple as with objects. We just call the functions as normal Python functions, but in this case, we define the file name and the value of the parameter. So we call the function with the name, the file name, and the content that we want to write. Again, we append some content and we read the file, and we call again to append. Okay, so we have it invoked. The runtime is smart enough to detect the dependencies among these calls. So you can see that this is write produces writes over f, and append, it's modifying, it's input output, while read file, it's input, and then we have append, which is input output. I advance you that this dependency that exists, the runtime will execute this first task, then it will execute this one, which depends on the first one, while read file and the second append depend on the first append, but they can be executed in parallel because this will take the output of this one, and this one will take the output of this one as well and produce a new result. So it's able to extract some the parallelism hidden within this order of calls. To retrieve data, to synchronize data, for the objects we use the COMPSs call. While for objects we provide the COMPSopen function, which retrieves the file and opens the file descriptor so that you can use it like the Python open call. Once retrieved, you can print the content and stop the runtime. The next Jupyter Notebook. Well, is there any question until now with files?
Javi, are you going to show the graphs that are generated, the task graphs at any moment?
Oh, I forgot to show the task dependency graph, the monitor.
It would be good to show.
I can do it.
Maybe for the next example or whatever, so they can see.
Yes, I can show it with now.
Thank you.
In the chat, there are no questions.
Okay. I forgot this, the comps monitor. As Daniela said, we have a monitor where we can track the execution of the application. And in the previous one, we can see the complete task graph. Well, this is very small. Okay, it's this one, for example. We see that that PyCOMPS has been able to extract the parallelism of the task and has detected the dependencies among some of them. This red symbol represents the synchronization of data, and the arrows are the dependencies of the data. The colors are used to define the name of the task itself. Okay, is this what you mean?
Yes, sure.
Okay. Okay, there are two two left notebooks. The first one is using constraints. Let's start the runtime. Sorry, I forgot to mention about the comps monitor. Here we have the monitor, and once which starts, then you can go to the comps monitor that I will show you later on how to start. You can refresh. It has appeared interactive mode 7, and you can get here the information about the resources, task information that are being executed to get the complete task graph, and you can see some more information about the execution that you are performing. So now, as you can imagine, a task is a single unit of work. It's a piece of code. And these functions may have individual characteristics that can be important for their execution. To define that a task requires something special, like for example, the amount of cores. For example, let's say that you define a task that internally does some inner parallelism, or that it is very memory consuming and you require an amount of memory for that task. We provide the add constraint decorator that has to be placed on top of the task decorator to define these requirements. So if we define a task that it is a square, in this case, we can place the add constraint decorator on top of the add task decorator, put the key that it is required for that task, let's say the number of computing units, the amount of memory, if it requires a GPU, etc. There's a ton of them in the documentation that are supported, so that the runtime is aware of the requirements of that function and it can select the appropriate resource where the task has to be executed. Imagine that you have some tasks that require to be executed within a GPU and some tasks that can be executed normally in a CPU, and you have different nodes. The runtime will execute the task that requires the GPU in the node where GPUs are, and the others depending on the load of the resources. In this example, I'm going to define 3 tasks, one which requires 2 computing units, one which requires 1 computing unit, and one last which requires 4 computing units. As you see here, I have selected to provide the trace. In the trace, we can see if the dependencies are respected because we have a graphical representation of the execution during time in the resources. So they have to be defined as normal tasks with the add constraint decorator, and then we can call them as normal functions. In this example, I am running with 4 cores. Okay, so this forces the runtime to say that if I am running 20 tasks of each of them, taking into account the dependencies, that it cannot place more than 2 square at the same time, because I have 4 cores and each of them requires 2. And whenever a multiply task is executed, it is going to require 4 cores. So no more than 1 task can be executed at that time. And the runtime ensures that. I will show later on in the hands-on how to retrieve the trace and how to check this kind of things. But it is important to know that the add constraint is there so that you can define the requirements for your task. Whenever you run with trace, it takes a while to stop, because at the end of the execution, it is generating that trace file that we will see later on. And I will guide you to open and play with it. And finally, to end up with this session, but it's taking a little bit longer than expected, I want you to show you the last thing with the syntax, which is how to define a task and an implementation. Imagine that you have a scenario where you have a task which is add 2 vectors, which has a constraint which is 2 computing units, and you want to provide to the COMPS runtime with another implementation. Let's say that you want to do this addition of 2 vectors using NumPy, for example, and it has some inner parallelism. You can place on top of the add constraint decorator the add implements, saying that the source class is in this case module, which is in the file module, and the method that you are going to override is add to vectors, and it has this constraint. Okay, then you can call during in your main code, you can call normally add to vectors, and in the particular case that there are enough resources enabled to use the implementation, the runtime can choose which one is the most appropriate to run. Let's say a simple example. Imagine that you have a task, an implementation, which can execute something with CPU, and you provide with the implementation running in GPU. If there's an empty resource with GPU, then the runtime will swap the execution and it will take the one with GPU instead of the one with CPU. Okay? And there's no need to call the add to vectors, the implementation in the main code. You just call to the add to vectors function, and the runtime will choose the other one if necessary. And the code remains exactly the same. At the end, we can get the results. Okay, so this is everything with this session. So
yeah, there is a question, Javi, from Diego. Is it possible to apply the constraint decorator later than at task definition? For instance, to determine the constraint at runtime based on the data, or to modify the constraint between calls?
this is an interesting question. It is possible to define that a constraint is going to be, for example, like an environment variable. You start with $my environment, but it can also depend in a global variable. If it depends in a global variable, then you can deal with this kind of scenarios.
But the value that we will get, it's the first one when we define the task. So you cannot, so the constraint cannot be changed. So when the Python code loads the code of the definition of the constraint, the value that we get for all the executions of this, it's this value.
Yes, it is
Okay.
it is static because that is registered the first time the task is called.
So what you can do is get a value of a variable or a global or an environment variable, but what we will get is at the value of this, for as a constraint, the value that this variable has at the moment of this
Execution.
task is loaded. So, well, this definition is loaded.
So inside one application, we cannot change it between multiple executions of the same application. Yes, we can change it. But it's something we talk about it, no, Jorge? Maybe sometime.
Yes. Mm-hmm.
Something, some kind of interaction between the user and
Yes.
and this.
So the first thing to do is to do git clone and this URL that I guess that all of you have already done.
Just one thing that if you are in the virtual machine and you have problems to copy and paste these URLs, there is also in the COMPSs bsc.es releases tutorial PATSI 2021. There is a commands text, I think, or something like This
Yes.
a file that you can find the
Once you have git cloned the tutorial apps repository, you will have a folder like this one, where you will have the examples for C, Java, and Python. It will be interesting to have because you can play with them later in the next session, so that you already have them. To continue with this session, first let's go into Python. Okay, and we have here some examples with plain Python scripts, but for the sake of this tutorial, we are going into the notebooks folder. Okay, now we are ready to start the PyCOMPS player with okay, I see that this is not shouldn't be there. Okay, now we are ready to start with start PyCOMPS player. Okay, so please go ahead and write this command: PyCOMPS init -i comps tutorial 2.8. Okay, if you have already done the Docker pull, it will be quite fast. Okay, the next command is PyCOMPS monitor start. So the first command is this. The second command is this one. It has started the monitor that I was showing you previously. Now you can get the URL, open your web browser, and paste it. When it asks for the username, write here root and log in with root. Okay. And now it's time to run PyCOMPS Jupyter. Like this. Okay. Here you will see another URL which points to the with Docker that instance that we have just started, and you can copy that address and go to your web browser and go to there. Now we can have in one tag the monitor and in another one Jupyter Notebook, and we can play with the folder that we have just loaded into the Jupyter Notebook. So now you can click in the hands-on folder. Oh, sorry, forgot to say. Within the syntax folder, you will find all the notebooks that we have been using in the previous session. And in the hands-on, we are going to see the ones for this session. Okay. So now, first of all, let's open number 8, sort by key, IPMB, and let's see a real application parallelized with PyCOMPS, which is going to sort the elements of a set of files and merges the results in the partial results respecting the order of all files. First of all, we are going to create a random data set we are going to create a number of files with some random data. For example, we define a function which is a dataset generator just for this algorithm to have some data to run, and we are going to, for example, to define what you want. For example, 8 files with number of pairs, let's say 100, and the directory name my dataset. If we run this, it will call the dataset generator, which will create 8 files, and each file with 100 pairs. Okay. If you go into the Jupyter environment, you can see that my dataset contains some data. Okay. Now, well, it is also possible to see it from here. Contains some data. Now you can import PyCOMPs and start again. Now it's time for those of you interested on seeing the task dependency graph. It says that the logs are interactive mode 01 within root into the Docker container. This path is into the Docker container, and you can go into the monitor, refresh, and select the name of the execution. There you see that it is by default using 4 computing units, 4 cores, and it is by now empty because we are not running any task yet. Okay, for this example, you can follow me doing click on the cell, and if you find any issue, then leave a comment in the chat. Then we import the task decorator and the file in parameter because we are going to consume files that maybe could exist, but we have generated randomly to make this example run. And we are going to define a first task, which is sort partition, which reads one file, which is data file, so that it is defined as file input. Oh, sorry, and that's another issue. Open SSL internal error. Okay, and we have this task which opens the file that has been defined as a parameter, sorts its content, and creates and returns, sorry, the sorted partition of that file. And then we are going to define another task which has which merges 2 partial results, list of key value pairs, respecting the order. It is interesting to see that this task is going to return a list. Again, it can work if you say returns equals one element. And there's a new label here, which is called priority. This priority label or parameter within the task decorator notifies the scheduler that this task is important and you want the scheduler to prioritize their execution. Okay. And finally, we are going to define a merge reduce function, which will create like an inverted tree and will merge 2 by 2. Okay. Then we can go to the main code. As well as in the previous, we import the const wait on and some other environment variables. We take the dataset path and we call for each file sort partition. We append the result into the partial sorted list, and then we call the function merge reduce with the task reduce task and the results of the partial sort of each file to generate the result. If we run this code with run, oh, sort partition is not defined. I missed executing this. Don't forget, like me, to run any cell. Now it says font task, and it finishes. It says the elapsed time, and you can check that the result is sorted by key. Now you can go, like me, to the comps monitor. You can go to the complete task graph. I think it's refresh. Oh, sorry, I said it wrong. Now you can stop the runtime. Sorry, because this is long. And at the end of the execution, you can go to the complete task graph into the comps monitor, because the task dependency graph complete, it is generated at the end of the execution when the runtime is stopped. If the execution takes longer, you can go to current task graph and you can see how it is, how the tasks are being in execution, pending, or being executed. Okay? And you can go into task information and you can get some more hints on the average execution time, how many of them in which resource, and so on. Okay? Let's go ahead and let's go to the k-means example. As you may know, the k-means is a machine learning algorithm very well known, which tries to group a set of multiple dimension points within a predefined number of clusters, looking for the closest center to each cluster iteratively. In this notebook that you can open by yourself and run each cell as me, following me, I will show you how this is done. First of all, again, we can start the runtime. If you go to the comps monitor, you can refresh. It will appear in interactive mode 02. Takes well, while it is working, let's continue with the k-means. In this example, I will show you the code of the k-means very briefly, and I'm going just to define the tasks that we have defined. For example, we have a function to initialize a random set of points, like a function to generate a fragment of points of the actual or total amount of points with a set of parameters, like, for example, the number of points, the number of centers, the number of dimensions, and the mode, for example, Karos. In this case, this function could be considered a task, but it hasn't been defined as a task because we want the point to be in the master so that we can plot them nicely and see the results. Okay? We define one task, which is cluster point partial, which calculates the distance of all points to each center. And another partial sum, which calculates the accumulated value of all the points belonging to a cluster. Finally, since it is an iterative algorithm, we need to reduce all the elements that we have calculated the accumulated sum. So we have another task. And finally, the merge reduce function, which merges 2 by 2. This receives a function as parameter, which will be the reduce centers task and all the data. Okay. The k-means algorithm requires it's an iterative algorithm and requires an stop condition. To this end, we are going to define the hasConvert function, which checks the distance of the points to the centers to see if it has reached the number maximum of iteration and that distance is lower of a predefined epsilon value to stop iterating. And finally, a very long function, which is for nice plotting the k-means. Please take into account for later that this function is only working for 2 dimensions or 3 dimensions. Otherwise, it won't plot anything. Okay, and now we go to the main algorithm. Here you will see that we have integrated this algorithm with widgets, with Jupyter widgets, so that the execution is more fancy and looks fancier for the user of this notebook. Okay. So, but the main k-means function is this one in this cell. This code is conditioned by a while loop which checks the convergence and iterates until the convergence or the number of iterations has been reached. Before the loop, it generates fragments because for normal data, for the input data, and then it starts iterating a parameter. First of all, it calls to cluster point partial tasks for all fragments. Then it calls for partial sum for all results of the cluster point partials, and then reduces the partial results of the partial sum. Here you will see that there's a synchronization of a single element and its normalization, which is necessary to check the convergence, to compare the new distance with the previous distance, you see. And finally, there's another loop that checks if we have lost a center to add a random one if one of the center has no points. Okay, that can happen since the initial centers are set random. At the end, we are going to synchronize again to COMPSs for the last clusters and plot them. Okay. So if you run this cell, it will show you these fancy IPy widgets where you can play with the number of vectors, the number of dimensions, the number of centers that you want, the number of clusters that you want to apply, the number of fragments, the distance for the convergence, the number maximum of iterations, and the seed for the data generation. And if you click in Run Interactive, it will start running. If you go quickly to COMPSs to the monitor, sorry, you go to current task graph, it's very slow in my machine now. It is very slow in my machine. I don't know why. You can check how it is being executed in your machine. And here in the Jupyter notebook, you can see the distance that it is reducing on each iteration until iteration number 14 with the given values that it has reached the best distance and found the 4 clusters here, plotted here. Okay. Now you are able to run again. If you want to change one parameter, for example, let's change the number of the seed, for example, and the number of vectors. So So we have less points, and you can run again the k-means with a different set of points. Okay? Let's see. Okay. You are also able to play with the k-means reduced chunks, which is exactly the same notebook, but the difference is that instead of having a reduction by pairs, it reduces a set more than two at the same time. Okay, but the algorithm is exactly the same. And finally, I have another example before giving you an exercise to run and play, which is the Cholesky's factorization. This is just another example for you to run and play a little bit to go uh, to play a little bit with the with Jupyter Notebook and Python. Again, we start the runtime. We import some needed libraries, and then we first of all we create random data. In this case, you can see that we cannot even play with MKL inside the functions, and we can define multiple tasks at the same time in the same cell. And for those of you who know Cholesky, these names will seem familiar. At the end, we have the algorithm for the Cholesky by blocks, and the main code is also is defined in this last cell, where we can define with also with widgets the parameters to execute the Cholesky. Okay, by default we have a matrix size of 8 blocks by 8 blocks, and each block has 1024 elements. And we can define the number of MKL threads that we want to use inside the tasks. Okay? This is interesting because in some scenarios where you have inner parallelism, some of the tasks can be defined with the add constraint decorator, and it will the scheduler will take that into account for not to do process overcommitment. So if you click run interaction, it has been really fast, so you can increase the block size, for example. If you run it again, it's small. Let's double the matrix size, and then it takes a little bit more. If you go to the well, if we finish the execution and we go, let me see if we have the graph and go. Yes. And go to the COMPS monitor, then you can go to the latest interactive mode. You can go to the complete task graph. Now it is loading the task graph. This task probably takes a while. And once it finishes, you will be able to see the task dependency graph. Okay, there you are. This is the parallelism that PyCOMPS has been able to extract from the Cholesky algorithm with these parameters. It has been able to extract complete parallelism from the from the blocks generation. Then there was a COMPS wait on, and then the Cholesky started. And those arrows represent the data dependencies that exist among tasks. Okay, This was for the first Cholesky that I executed, and for the second one, oh, sorry, is there. Okay, so now it's time for you to play a little bit with one exercise. For this exercise, we have prepared a very, very simple exercise, which is the word count exercise. And we want you to take a set of documents that we provide and count the words that there are on all of them, in all of them. Okay, so you may think in a structure like this. Okay, the parallelization, as a hint, it can be divided into two phases. First one to count the words of each document individually, and the second phase to merge all the results in a single one. So if you open, well, now I recommend you to select the ones that you have already opened, shoot them down for not to slow down the machine, and open the word count exercise IPMB. There you have an example of a sequential version of word counting, which has a function for reading files, for word counting, another function for merging two dictionaries, and the main function. The current path to dataset already contains the files to be counted. Okay, so let's solve this exercise directly online. Okay, so the first thing that you may have done is to, from PyCOMPSs.interactive, no, sorry, import PyCOMPS interactive as a PyCOMPS. And then you import the PyCOMPS library, and then you start the runtime. PyCOMPS.start, let's say graph equals true, and monitor equals 1000. So it will refresh every second. Okay, so now we have the runtime running. Now we can import the task decorator from pycoms.api.task import task. Okay, but since we are working with files, we will need the file label, the file parameter from pycoms.api.parameter import file. Which direction are going to have the files? Since the files already exist and we are going to consume them in the read file function, they are going to be in direction. Now that we have imported, we are going to import the OS library, and now we have the read file function. Can this function be a task? Yes, it can be a task. If we decorate this function with the task decorator, it returns a list, and the input of the task, which is file path, is a file with indirection. Okay, let's initialize it. The word count function can be a task. I guess so, because it is executed over every chunk of data retrieved by the read file. So if we include the task decorator and we return, what it returns? In this case, it returns a dictionary, but you can say, for instance, that returns one element or a dict. And the input data is an object. So there's no necessary, it's not necessary to put anything else. The next, we have a function which merges two dictionaries. Can this be a task? Let's define it as a task because it receives the input of two partial results. Task returns dictionary, and the input, they are objects already. Now we can run this cell and we can go directly to the main code. Okay, what happens if we run this code now? If we run this code just now, it will say that it has found some tasks, but the results, it says, hey, this is a future object. I cannot I cannot sum the results of the values. This is because we have not synchronized the total result. Okay, so we need to synchronize the final result. So to this end, we need to import the synchronization main function, which is from PyCOMPS.api import comps wait on. Okay. And if we go to the algorithm, we see that there's a for loop which iterates over the files. It calls read file with the path. The data generated is the input of the word count function, which is appended into the partial results. So this list will contain the future objects or work on the data. And then there's a second loop which iterates over partial results list and merges all of them, the result with the next partial result. And what it is missing here is to do result equals comps wait on result. If we run again this cell and we check the results, then it has worked perfectly. If you want, now you can go to the comps monitor because we started, you can refresh and you can go to the interactive mode number, the last that you have executed. You can go and check the task information and it says the number of executed tasks. The current task graph will be empty because there are no tasks running and the complete task graph has not been generated yet. If you go to the exercise and do the last thing needed, which is to stop the runtime, PyCOMPS stop, you stop the runtime, it says that some variables may have not been brought to the master because there's no synchronization here. The execution is finishing, and once it finishes, you will be able to check here, because it has finished, the execution, the task dependency graph. There you go, we have run twice, but the first time without the synchronization, so that we got the error, and the second time synchronizing it, and we got the actual results. Okay, so we see that it has retrieved only the last element of the merging. So the parallelization that he has been able to to get from this algorithm is that it has been able to read all files completely in parallel, all the white circles, which are the the word count, they are also completely parallel, and there's a dependency among them that it's the critical path with the reduction. There's another alternative to to solve this exercise, which is to apply a reduction like in the word count. If you like in the k-means, like pair by pair. If you go into notebook number 11 word count solution with reduce, you will have here again the word count solution. Let's run it, and there's a slight difference with how the reduction is done. It receives a number of dictionaries at the same time. So now if we pass all partial results to these merged dictionaries, it will receive all of them, and it will wait for that result. It has given the same results. It has just finished, and you can go to the comps monitor, refresh, go to the last execution, and you see here more clearly that this implementation has the same parallelism for reading the files and for computing the partial word counting, and at the end, all partial dictionaries are merged in a single task, which is executed remotely, and the results are then retrieved to the master where the results have been plotted. Okay, any question until now? There's a good question in the chat, which Alejandro Fernandez is asking, what was the meaning of priority parameter in the task definition? The priority parameter tells the scheduler that that task is important, and it can it will try to execute it as soon as possible when there are multiple tasks that can be executed at the same time. Okay, so wrapping up to finish this session, just to give you the most important things from PyCOMPs, is to point out that if you have a Python sequential code, you just need to focus on defining which parts of the code do you want to define as tasks, then declare them with the task decorator and add the appropriate comes with on synchronization calls, and the rest of the complicated things like the task of loading, data movements, it will be automatically done by the comps runtime. Okay, so thank you. No, Diego is asking if PyComps only supports built-in data types. No, it also supports user-defined data types. In fact, this is a very good question, because if you go, for example, this is a very good question. If you go and you define your class, you have your class shape, and then you define a task that returns shape, like this is completely supported. And the interesting thing of this is that if you create a shape, like if you call this task, let's say result equals my task, then you are able to do result dot perimeter, for example, and call an inner task. In this particular case, result will not be a future object, will be an instance of shape, and you still can run tasks defined within the object itself. And this and the PyCOMPs will detect that there's a dependency between this task and this task, and there's no need to do a synchronization among them.
Also, there is a condition, right? For the objects, they have to be serializable.
That's true. That's true. All data types must be serializable with pickle or pickable. But for those user-defined data types, it is possible to implement the set state and get state for those objects to make them pickable.
There is another question from Manuel.
Yes.
Is filing the default for file parameter if you don't specify it?
If you don't specify it, it will take as a string. But if you specify, instead of filing, if you specify just file, like, sorry, this, in the exercise, if you specify file, it is considered as file in. So this is equal.
Yeah, the file is required to distinguish between a string or a file name.
Exactly.
Okay. Paolo says, is it possible to run a Python script containing PyCOMPS decorator from command line? And how to specify the configuration file?
Yes, it is possible. And this is what we are going to do tomorrow in the Mare Nostrum 4 supercomputer. To this end, just to give in a little spoiler, we provide two commands. One is runComps and enqueue-comps, which allow you to run a Python script containing PyCOMPS decorators. The only difference between those scripts, Python scripts, and the Jupyter notebooks is that in the Jupyter notebooks, you need to explicitly start the runtime and stop the runtime. Using Python script, this is not necessary. The Python script just contains the task decorator and synchronization, and that's it. And how to specify the configuration file, it depends on the environment that you want to run. But if you ask for the flags that we use in the start, they can be defined in the runComps or enqueue-comps commands.
Yeah, okay. There is another question from Vishan. Is
Yes,
there a documentation online to read more about PyCOMPS decoration?
yes, we have the PyComs at read the docs. I'm going to paste the latest documentation command, which is this one. And here in the documentation, under the application development, there's a Python binding, and here within this label, you will find all the programming model where you will find everything and all the small snippets for defining task constraints and all of the things that we have shown here in the tutorial and probably a little bit more. Okay.
Okay. Another question from Katarina. Can you show again how you called a function from shape my task?
This one?
You can unmute.
Yes, that's one. Thank you.
This one. So this is supported. And my task, this one, this is a task, and this is another task.
Another interesting thing here is that if you see the object the shape, it's created inside the task. So if you are creating a very large object, one thing that is interesting is that you don't create in the master and then you transfer. This is created in the worker, and here you only have a dummy object.
This result is a dummy object which is very small in memory, while it can be very big in the worker node. And you then the next task perimeter is called in the worker over that big object.
Yeah, it is interesting if you call several times this my task, because if you run this sequentially in the master, you could go out of memory. But with doing this, you create the objects in the workers, and then you have more memory because you have all the workers' memory to create the objects, and you only have the like a representative in the master, but not all the objects. Okay, another question from Paolo. Why does result my task get executed immediately? Well,
This is a good question,
yeah.
and because my task will return a shape object, a default shape object. This result will be a default, and we know that this default is actually the object created by my task. It's just the reference to this result. Since this result is the default object constructed, like for example, let's say with the default constructor, because in this case there's no default constructor, it should be like, to avoid, to be completely sure, it should be like this, and then you can call shape and it will create a default result. Then this object, which is the default constructor, default constructed shape object, exists here, and we know that this is the reference to the actual result of my task. So then we can, if we detect that there's another task over this object, we know that the target object that you are calling is this one. So we are using result just as the reference for the output of the task.
And also, just to clarify one thing is that the my task is not immediately executed. we create a node in the graph, and once we have a resource ready to execute, we will execute this. But during this time, what we provide is the result is just a reference to enable to execute more the following tasks without having to wait until the result of the my task. I don't know if it answered your question, Pablo.
Yes, so basically at the end, you will execute these tasks. They're not actually, well, at the end when you run the comps on wait on, right? That's when you actually execute.
No, we can execute before, but in comps wait on is when we wait for the results. This is not like a Spark or something like this that you create all the things and then you put collect. In our case, we can start to execute. If you have empty resources, we can start to execute the tasks. Okay, but it's asynchronous. It's not at the moment that you write, but it's not also at the moment of the comps wait on. It's in the middle. We cannot ensure when a task is going to be executed, but what we are doing with comps wait on is synchronizing the data. So we will wait until the task that is generating this data has finished, and then we collect the data.
Thank you.
You're welcome.
Yes.
More
For example,
questions?
in the word count, we only wait for the result, which is, by the way, the produced by the last task. But we are only retrieving result. We are not retrieving any partial result.
Yeah, when we synchronize the data, you have to be you have to take into account this, that when you, if for instance, you can do the same workflow, doing task wait on, so this kind of loop, and this is not creating parallelism. But if you do a for loop of all the task invocation, and then you do all the for loop for all the wait ons, as we do more or less in some examples, this will create the parallelism, because all the task invocations are independent, and you will spawn all the tasks. And then when you are starting to do the wait-ons for all the tasks, what you are doing is it's synchronizing for only one of the tasks. So you don't need to wait for all the tasks.